Hello. In today's video we're going to be looking at pKa for monoprotic acid and polyprotic acids. We're also going to be looking at indicators, that's what we're going to actually start out with, is looking at our indicators. Okay, oops, oh, sorry. Okay, so indicators are used in order to visualize the equivalence point of a reaction. They are used in acid-base titrations all the time to give people a better idea of when they're getting close to that titration point, or the point at which they are at equivalence. And each indicator has its own range of pH values that it changes color. So two common indicators are phenolphthalein and methyl red, which I've shown here. The one on the left, or the one on the top, is phenolphthalein. The one on the bottom is methyl red. If we look at our phenolphthalein, the one that's pink, we see that it has an equivalence range between about 8.5 and 10, or a color range between 8.5 and 10 pH units, which means that as you get close to that pH of 8, you're going to see a color change occur. So phenolphthalein indicator is really good for something that has a basic equivalence point. So if you're doing a weak acid titration with a strong base, phenolphthalein would be the titrate or indicator that you would use for that. And then methyl red is another option. Methyl red has a pH range between 4.2 and 6, which means it changes colors in that range. And it's actually orange in color, pink or orange. Orange if it's really basic, or sorry, really acidic. Pink if it's, or sorry, yellow if it's a little less acidic. So it's good for an acidic titration, such as a weak base with a strong acid. So there are other indicators outside of this, but these are the two most common for our weak acid with strong base, or weak base with strong acid. So if you want to do a titration of a weak acid, you're going to use phenolphthalein. And if you want to do a titration of a weak base, you're going to want to use methyl red. And of course, these can also be monitored by just a pH probe, but the color change makes it a lot easier to get very accurate results, because you'll start to see as you get close to that range. Okay, so when we look at a pH curve for a strong acid versus a weak acid, they're going to have different pH curves, or titration curves. For a strong acid titrating with a strong base, we get a large S curve. So what we see in red here, going up to the blue. And then if we compare that to a weak acid titrated with a strong base, it's going to be this blue curve. So the first part prior to equivalence is going to be where we have the most difference between a strong and a weak. With our strong, it's fairly flat and a slow increase. With our weak, we have this curve that we see. Another interesting thing that we see only in a weak acid is at half equivalence, so half the volume that it takes to get to equivalence, our pH is equal to our pKa. We also, for a base, POH will equal your pKb at half equivalence. So you can very easily look at your pH curve for a weak acid or a weak base and determine the pKa or Ka of that substance. Another difference between our strong acid and weak acid titration curve is our equivalence point. The equivalence point for a strong acid will be at 7, and the equivalence point for a weak acid will be more in a basic region. And the weaker that acid, the more basic that equivalence point will be, which is what we see over here in this graph. So as we go from a fairly strong weak acid to a fairly weak acid, we see that our kind of curving point becomes more intense or more prevalent in our weaker acids, and our as our Ka value decreases, our pH of equivalence increases right here. So you should be able to recognize the differences between a strong acid and a weak acid titration curve. And all of this will be the same thing for a weak base. It'll just be opposite. So a strong base titration curve looks like this. A weak base like that. But the bottom part, or top part, the part where we have just the titrant, after equivalence is going to look the same whether we have a strong acid or a weak acid, a strong base or a weak base. Okay, so let's try a practice problem. So we've got the following titration curves, A and B, and we want to know which one is a strong acid, which one is a weak acid, what is the equivalence point, or pH for the equivalence point for each of them, and then the approximate pK for the weak acid. So if we look, B has a straighter curve down at the bottom, so B is going to be our strong acid, while A will be our weak acid. We can see that curving up that we expect to see with the weak acid. So A is going to be our weak acid. Then we could look, if we're looking at our equivalence point, we're basically going to take the top of this equivalence region, the bottom of this equivalence region, right there, divide it in half, right here. Sorry. And we'll do the same thing for this one, right here, and right here, and get equivalence volume somewhere right here. So for our strong acid, it'd be about a pH of 7, and our weak acid, a pH a little bit greater than 8. Then we want to know our approximate pKa for our weak acid. So I'm just going to do a little erasing here so we can see it better. So our pKa, we're going to set it equal to our pOH at half equivalence. So we see that our equivalence point is at 30 milliliters, so our half equivalence would be at 15. So at 15 milliliters, we have a pH of, 4.5, which is equal to our pKa. Okay, let's real quick look at polyprotic acids. So polyprotic acids, you're going to have two sequential titrations. So you're going to lose your first proton, and then your second proton, and then third if it's a triprotic. So you lose each proton sequentially. So we have either a diprotic acid, so we have two acidic protons, and you're going to lose each proton one at a time. And then you have triprotic, which has three acidic protons. So, with the number of protons, you'll have that many equivalence points and that many buffering regions. So, this will have 2 equivalence points, and 2 buffering regions. unless we are talking about H2SO4. H2SO4 starts out as a strong acid, so it will only have one buffering region, but it'll still have 2 equivalence points. So H2SO4, 2 equivalence points, 1 buffering region. So it looks a little bit different for them. For our triprotic acids, we're going to have 3 equivalence points and 3 buffering regions. Okay, we don't look at triprotic very often. We generally just look at diprotic, and we won't do a triprotic titration. Okay, so you generally treat this the same as you treat any weak acid. Again, H2SO4 is different, but you're going to treat these the same as any other weak acid, except H2SO4, which is strong to begin with. Okay, so here would be an example of a weak acid that's diprotic. We know it's diprotic because it has 2 equivalence points. And we know it's a weak acid because of the kind of curving of the regions, and the fact that we have buffering regions. So we have 2 buffering regions. Each of those buffering regions, we have our pH equal pKa, so we have our pKa 1 equal to 2.34, and then our pKa 2 equal to 9.69, and we can use that information for both of them to determine what our equivalents, or what our Kas for these substances are. Okay, so we also see 2 equivalence points for our 2 hydrogen losses. So this would be an example of a diprotic acid. Another thing to note, our first equivalence point is always going to be a lower pH than our second equivalence point. And we don't look at titrations of dibasic bases, only diprotic acids. Okay, I think that's it for this video. So I'll see you guys later.